Hello, my name is Hanbin Ko, and I'll be presenting our paper, Temporal Inversion for Learning Interval Change in Chest X-rays. So radiologists don't read chest X-rays in isolation. When a prior exists, they report how findings change. Here, the vision is new, it's worsened. So to learn progression contrastively, the model needs the same finding in different directions. If vision improved versus if vision stable, a different finding doesn't help. But in practice, batches contain different findings, so the model takes a shortcut. It discriminates by which findings appears, not by how it changed. Progression is never actually learned. So how do you fix this? Our key insight, swap the order of prior and current. When you swap, improved becomes worsened, and stable stays stable. If you train the model on both directions, it can no longer shortcut. It has to learn that order carries meaning. One caveat, not all findings are clinically reversible, so this should be used with care. So our contributions are threefold. First, Tyla, applying temporal inversion across pre-training, fine-tuning, and inference. Second, an inversion-aware evaluation protocol that tests whether the model surely reasons about temporal order. And third, consistent gains across tasks, datasets, and architectures. Here's the overall Tyla pipeline, with inversion applied at every stage. Let's walk through each. So before pre-training, we need a change label for each image pair. We feed the prior and current reports into an LLM, which decides whether the patient's condition changed between the two studies. This binary label drives the pre-training objective. Now that we have the change labels, we pre-train with a SIGLIP objective. Standard SIGLIP treats diagonal image report pairs as positives and everything off diagonal as negative. In parallel, we encode the swap pair. Current first, prior second. Here's the key change. The swap pair is positive only if there is no change in the report. If the report describes change, even the diagonal pair becomes negative, because the swap reverses the described progression. We add the two losses. Fine-tuning classifies the pair as improved, stable, or worsened. We apply cross-entropy on the original pair and on the swap pair with the inverted label. We call this bidirectional cross-entropy. TCL adds one more constraint. The forward and reverse probability distribution should be mirror images. At inference, we average the forward prediction with the inversion adjusted reverse prediction. When one direction is uncertain, the other often isn't, and averaging pulls the score towards the right answer. We also introduced MSCXRT retrieval, a new benchmark that reformulates MSCXRT for retrieval. For each pair, we generate three directional variants, improved, unchanged, and worsened, isolating progression as the retrieval target. So we apply TILA to two paired image backbones, biofil T and alpha, both designed to encode prior and current scans. We use four evaluations protocols: standard, classify on the original pair, reverse swap, and predict the inverted label; combined, average forward and reverse predictions; and consistency. Correct only if both directions are right. So starting with retrieval, paired image models outperform single image ones on TEM score, the temporal alignment metric, and TILA pushes TEM higher on both mimic and expert, while recall K stays comparable to the baselines. Temporal gains, no retrieval costs. Our retrieval and zero-shot TILA improves over the baselines, and combined scoring adds a further boost. In the supervised setting, TILA improves standard accuracy, the clinically relevant metric on both backbones, and combined improves it further still. The reversed and consistency gains tells us why. The model is now genuinely reasoning about temporal directions, not just exploiting label priors. MSCXRT labels each cases as consensus or disagreement. Disagreement signals as ambiguous case. On consensus cases, TILA sharpens the margin between classes, Confident answers when the ground truth is confident. On disagreement cases, it stays conservative, mirroring radiologist uncertainty. For ablation, adding tile components one at a time, just swapping the stick lip barely helps. Adding changeover stick lip gives the largest jump across all four metrics. BICE and TCL add fine-tuning, further refine directional sensitivity. And finally, binary interval chain screening, a clinically useful triage task on seeing did anything change between the two scans. On the private cohort, Tyler improves AUC modestly, but on Rex gradient, the baseline collapses to 0.565, barely above chance, while Tyler holds at 0.702. So to summarize, temporal inversion is a free, label-aware supervisory signal for paired image VLMs, improving directional reasoning without sacrificing standard accuracy, and transferring well to binary screening. So some caveats: progression labels are noisy, and not all findings reverse clinically. For things like fibrosis or post-surgical change, pre-training still works, but fine-tuning and inference need care. So future work, multiple expert consensus labels, and longer longitudinal sequences. So thank you for watching. If you have any questions, feel free to reach out. Contact details are on the slide. Thank you.